Alright, good evening everybody. Yeah, so let's solve some questions. So this question was basically asked to find the chromatic number of a graph. It's notoriously tricky finding it exactly, then be hard for general graphs. Systematic ways, okay. Complete graph. That is the first approach that I have gone through. So K in chromatic number. But this is not a complete graph because this vertex is not connecting to this vertex. Similarly, there are a lot of other pairs of vertices that are not connecting to each other. So cyclic graph, it is not a cyclic graph as well. If a cyclic graph is even, then the chromatic number is 2. If it is not, then the chromatic number is 3. So you can just take the example of a triangle and a square to get that. And bipartite graph, this is actually important. Bipartite. Use bounds the largest size, the size of the largest click. Okay. Greedy coloring and special tricks planar graphs. Chromatic number is less than or equal to 4 by 4 coloring theorem. Chromatic number is equals to click number for a perfect graph. Perfect elimination order in coronal graphs. So there is no easy universal formula for all graphs. Okay, click size. So in this one, the answer set is a bipartite graph and how to find if it is a bipartite or not. Graph is bipartite if its vertices can be split into two disjoint sets such that each edge is connected to a vertex in U is a vertex in V, which connect vertices within the same set. So the graph is bipartite if it has no odd length cycles. Okay. Pick any vertex and assign its color 1, assign its neighbor color 2. Continue BFS or DFS if any neighbor already has the same color. 2 coloring test. So 1, 2, 3, 4, 5. My bad. 4. 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4. 1, 2, 3, 4. Okay, 1, 2, 3, 4. 3, 4. Yeah, 1, 2, 3, 4. Okay. Traces are always bipartite. Wow. to color the graph using BFS or DFS. You can use two coloring test, okay? Two coloring test. We will check that one out. So this is question number 2, by the way. Okay. So let's see if this thing is too colorable. Wow. I missed a lot of these things. So let's do this red. And let's put all of its adjacent vertices to blue. This is blue, this is blue, and this is blue, and this is blue as well. 1, 2, 3, and 4. All right. So we have done the coloring, and can we have any other? Okay. But I will check it out. So you told about the algorithmic check. Can you help me about that? Like how to do that? Pick a starting vertex. Okay, color its neighbors. For each vertex, check its neighbors. Okay, so that is what we did. So this is the neighbor, and we are thinking of assigning it red. And this is the neighbor, and we are trying to assign it red as well. And this is the neighbor, and we are assigning it red. It is really as simple as that. Wow. So red, blue, red, blue, red, blue, red, blue. That's it. It is actually a two. All right. It is actually a pretty simple question. We just messed up. So can you color the Peterson graph in this way? Let's see. Peterson and Herschel, right? We got it. Yeah, this is a Peterson graph. So let's color it red and let's color the other things blue. So this should be blue and this should be blue and this should be blue. These are the adjacent vertices. And now scan for other vertices of these. So this should be red and this should be red. But did we get a controversy yet? So, and this is adjacent vertex. This should be red and this should be red. But red and red. We got a controversy. It is not too colorable. Not too colorable. So how do you check if it is 3 colorable? Let's take Peterson graph with this as example. It obviously is not 1, 2, 3, 4, and 5 by Bartlett. Then how do you proceed with its coloring? We cannot do color it. Regular of degree 3. Each vertex has a degree 3, contains odd cycles. Click number is equals to 2. Okay. What is click number? This is known result. Pick a vertex, color it red, color its neighbors, they must be blue. Neighbors, okay. So, what we are trying to do here is we will pick 3 colors now. So, red, red, blue, blue, and the adjacent vertices should have red color. It is not too colorable, I just got it. So, this is red, and if you put this as red, no problem as of now. And what are its adjacent vertices? So pick this one, and if you put this as red, it is going to clash. So let's put this as green, and this can be red, no issues. And now pick another vertex. So this is blue, and this can be red. No, it cannot be red. So it should be green, and now it is blue. It cannot be red. It should be green. Okay. But green and green, we got a conflict. So this cannot be red and this cannot be green either. So this greedy method is not going to work out. We need to go through a lot of iterations. You need to backtrack a lot of times. You can still use 3 colors and not able to properly color the graph. So how do you do it? Just knowing that. Now you greedy can trap you. Okay, you know what? We will not get into that theory because it isn't be hard. We got that question. It is a bipartite graph. It does not contain odd cycles, so it is two. And you can use the two coloring method to check if it is two or not systematically and easily. That's it. Full stop. Okay. Group of integers from 0 to n minus 1. So there are n integers with the addition modulo n as group operation, the number of elements in the group. Okay. I don't know group theory in the first place. What the heck? Wow. Basic set theory and algebraic reasoning. Like addition or multiplication with a certain property solved closure. Take two arbitrary elements from the set, apply the operation. Okay. Integers under zero group. Integers under multiplication. Non-zero rationals under multiplication. Yes, sir. P by Q. Natural numbers under addition. Okay. Matrices under multiplication is a group because invertible matrices. Addition modulo. I did not understand the notation like addition modulo and addition modulo 5. Mm-hmm. Okay. The number of elements Z2 has two inverses. I don't know what this guy did. Every element must have an inverse with respect to other. For addition modulo, the inverse of A is number B. Okay. Okay, this question is actually not wrapping around my head. So basically it is saying it is bijective. No, I don't even understand what these people are talking about. Okay. Wow. Yeah, I have done this one actually. So that is a square is equals to y. So path of length, that means walk of length 2 is equals to walk of length 2. So that will be this. Number of walks of length 2. That is what it gives. So we need to understand graph theory. J is a cycle. For a matrix A, if it represents the adjacency matrix, then what is for every vertex I, there is exactly one walk of length 2 back to itself. So what he's saying is from this is I, this is j, and from I to I, 1 and 2. From I to j, the walk length is no. What is a walk in the first place? But this would give I to j. Let's say we got A, B, C, D. A, B, C, D. If you have something like this, A to A, the two path walk is 1. Okay, the two path walk. From A to B, the length of two walk. No, there is 1 or there is 3. But there is no 2. So that is 0. From A to C, there is no path A to D. Wow, you got it. So what now? This is partial ordering. Number of total orders. Okay. Comparable. Did we do this question properly? No, right? I don't think we did this question. We just read this question and we went. As if I remember, this is the only question that we did properly. Yeah, maybe we have this one here. Yeah, okay. Partial orders, yeah. So we are here. So every possible order pair, 1 1 2 2 3 3 and 4 4.